glad you're here. I'm Jen Lepore, Marketing Team Coordinator here at Custom Processing Services. And today we're talking about how do you push throughput on high performance materials without letting your specs slip. And joining me today is our own at Custom Processing Services President Gregg Shemanski. Gregg not only brings years of industry leadership and experience, but has worked closely with customers processing some of the most demanding materials in energy space, such as battery powders, functional additives, and especially particulates, where even the minor drift from spec can mean the difference between product that performs and one that doesn't. So thanks for being here, Gregg.
Hi.
So let's kind of start here with core tension. So let's start from the beginning with core tension. In advanced powder processing, companies are always being pushed to produce more faster. But these materials, especially battery grade powders and functional additives, come with extremely tight specs. So Gregg, how do you often see throughput demands working against product consistency?
We don't at our company, but we did that with a very specific, very focused way. If we were to manufacture something in a production station, a production mill, a processing station, and need to increase throughput rate, we've done this in the past while maintaining these specifications, because there are critical parameters within the process that must be maintained in order to maintain whatever element we're looking for, whether it be the narrowness of a particle distribution, whether it be the roundness of a particle, whether it be the top size as a critical absolute cut, whether it be the maintenance of density, sometimes even color gets changed. But all of that is considered, and many times combinations of that are considered, if you know the key operating parameters of your machine. In the past, we have done design of experiments to make sure that we can identify the critical elements that will control all of those really important parameters, and documented them, tested them. Our machines are built with technology of formula. There's thick books of calculations on how the theoretical operation of our mills go. So we can do that from a very small, even theory, and then when we need to go faster, we can add all the parameters in at the right way. Most of it is the energy per kilowatt of product, kilowatts per kilogram of product that we're making, or kilowatt per ton of product that we're making, depending on how fast it's going on, and still maintaining that very important particle. I know there's a lot of people out there, and I've done it in the past, early in my career. I've been doing this for 44 years, and realize that being able to scale something from small or even production, but then even when you're in production, to go even faster without changing the distribution of or the shape or size, the critical element of the final product you're looking for. And it's taking some science, it's taken historical knowledge on this, but it's we understand it, and that's the thing that lets me sleep at night, knowing that we can make something twice as fast and still have it be identical in its shape, size, and tension.
Great. So, what makes advanced energy powders particularly unforgiving compared to other materials? Is it particle size distribution, surface area, chemical reactivity? What are some of the critical variables customers have to protect there?
Well, you must tee that up, because it's all of those. Especially with energy storage units, you want to have a high density of power to the density of the material. So if you can make a compact, you only have so much space in a battery. If you can develop and gain as much material as you can in that energy, in that space, in that volume, and develop more energy for all of that, that is best. So density of the product, bulk density of the product, flowability to get it into those spaces, the particle sizes that do that are critical. And in some instances, like graphites and such, where there's a lot of different, flake graphite doesn't play out very, very well. So spherical graphite makes a dense particle, and it transfers the energy quite nicely. So the shape of the product, the tightness of the distribution of that product, and always trying to stay away from very fine materials that will impede flow or impede the bulk density of that set of products so that your energy density goes low. Those are key numbers. Too big, you'll have shorts and whatever else in the energy. So that's why a nice, tight, narrow distribution is there. And we've seen that. We've been there. And there are different types of machines that we use to do different types of processing to get what the customer wants. Every storage battery, every mix of different materials, let's call it a different way, matrix of materials, would require different particle sizes to optimize depending on what it's for and what raw materials are being used. And we can get very tight as to what the customer may need, but you have to think of it. There's a lot of the research and development chemists would come to us and say, this is the material I have, this is what I have to use. But I'm surprised to find out that a lot of them really haven't done a bulk density check, a surface area check, a particle size analysis, a fines distribution curve, a solubility, and anything, a dryness. So we categorize it at first, and then we help them define it to what they need. They'll tell us what they want. We'll get it there for them. But to start with what they have and realize you don't have to use what's on the open market as it is. You can convert it, you can conform it, you can classify it, you can grind it, you can disperse it in different ways to make what you are looking for and make it work well. So that's, and they're big payoffs if you do that the right way.
Awesome. So when a process is in spec at a smaller batch, what exactly happens to those variables when you start pushing volume? Where does the drift usually show up at first?
It doesn't have to if you're thinking through how that machine operates. If you don't, the drift happens if you don't have all of the key operating parameters moving from lower throughput rates to higher throughput rates in place. Like I said, there's the amount of energy per kilogram of material that's going to be out there that we have to put into a product. That has to be maintained. There are velocities of the grinding actions that are happening inside any grinding unit. They have to go up identically with it. There are airflows for classification, rising velocities, classifying velocities. All of those have to be maintained together. If you do that right, it'll be good. If you're off on one of them, you might find that you're going to get too many fines in the product. If you're off on one of them, you might find that some of these particles just drift on the top size, or you try to control top size but wind out with a wider distribution. These are all correctable variables, but if you know what the machine is and know what it's going through, you can put a big throughput right out. Ours is, we're straight line from little tabletop to production size. The biggest variable, honestly, that we're finding, Jen, is the raw material coming into us and how it starts. Now, we can normalize some of the variability in raw materials to make a good end product. So we're correcting a lot of flaws that happen with that, especially with the ability for it to flow or pour or pack. We can normalize those things. And that's the neat part about what we're trying to do.
So would you say there are specific points in milling and blending, drying, classification processes where throughput pressure creates the most risk for spec deviation?
It could be any way, any type. That's what frustrates people, right? Mm-hmm. I've gone from small batch to big batch and it's too big. We can fix that, but without correcting all the rest of the parameters, you might shift the curve. It's not any one thing that you have to control. It's all of it at the same time. It's a process system. It's not a process point. And there's a lot of variables inside there, and you have to watch them. So when people try without knowing this and just, let's twist this button and just this knob and see what speed of this machine makes this material look like, and they just try it and grasp at something and say, I'll see what happens. it's backing up a little bit more and understanding what that machine is, because all of a sudden it'll be, well, if I turn this up a little bit, the distribution goes wider, or the top size went out of spec, so I got the top size in, but now I have too many fines, or I have stopped the number of fines, but my throughput went back to low again because my carrying velocities aren't there. Those are all the way things that you can correct. But if you start it in a small unit, don't be afraid of a tabletop unit in giving you enough data. Is it a direct upscale for what the throughput would be? Not always. It's too small. But the parameters that it operates under are there, and they're very measurable. Use them to make good big product, bigger machines. Pushing a throughput rate in an existing machine is going to be limited by the ability for it to have its electrical horsepower that's connected to it, whatever the grinding power that's connected to it, and the airflows that it can see as you're processing, especially these critical powders. And it's only limited by that till you need to go to another frame size and go up again. But jumping a frame size doesn't scare me, a bigger mill, a bigger process. But pushing the most you have out of the machine you've got, you just have to watch that all the control parameters are equal. As throughput goes up, what is the effect on power per kilogram? As the airflow goes up, what is the effect of volume of air per kilogram? Those types of items. It's actually a fun little puzzle to do all the time.
It sounds it. So let's kind of go into where optimization attempts go completely wrong. So when customers try to self-optimize to get more throughput, what are the most common mistakes you see? You know, are they adjusting the wrong variables, or is it more about not fully understanding how those variables interact?
In the end, it's not understanding completely how the variables they're watching interact with variables they might not be watching. There are pressure drops within every system, and a lot of times they've got to be looked at critically. There are airflows throughout the system on the feed end and then on the final product end that need to be watched and looked at consistently. There are heat zones that what happens, because especially these high performance materials, whether they're in the energy industry or the high value polymers or high value minerals, they affect what this particle can look like too. So it's watching it all. The first thing you try to do is just put more throughput for the same amount of power going in, or just put more power to it. I'll take a 100 horsepower motor and put a 150 horsepower motor on, and I'll crank all 150 horsepower out of it. It doesn't quite do it, because all the rest of these variables have to come into it also. So the idea is correct. If I put more energy in, I'll get more out. But what is it doing to your distribution?
Makes sense. So do you think some companies sometimes look at batch optimization as one variable problem, like simply running faster or increasing batch size, when in reality, there are a lot of interconnected factors that impact the overall process?
Well, some of these are continuous processes. Mm-hmm. So it would be a batch of material going through as a continuous process. Or there are some that are in dispersions or blending that batch to go bigger from a small blender or mixer, especially in a lab, to go to a large one in a plant, or even a bigger one after that, or trying to reduce the amount of time a batch takes to blend by adding more speed or power or turns or cycles, it can become a problem. So making bigger batches, as long as all of your parameters of mixing are identical. I've been talking a lot about grinding, but if you're mixing tip speeds, if you're mixing temperatures, if your amount of touches that the material has with whatever blending unit it's seeing, how many turns it really is seeing inside that particular blender, they all vary. They can be very upscalable. We have a 100-liter blender, and we can watch and know what we have with that. And then when we go to our 7,000-liter blender, we can get the exact parameters we need, because we're watching the critical points of turn time, amount of work, amount of speed it's seeing, the rate at which we're adding any products or holding the products, the temperatures we're seeing, the airflows going across the unit. All of those items make a big impact. If we're dispersing, there's a lot of dispersion type of issues that would go into it. I mean, there's a theoretical tank size versus the mixing size versus the speeds, the tip speeds, the amount of work you're putting in, the vortex you've got to create, all of those types of items to make a liquid dispersion, and then to make mud, the same kind of items, maybe without the vortex, but are all critical in what they're trying to do. It's not so hard. Watch what's happening at the small units and make sure all of the critical parameters are done in the big unit.
You kind of are going into my next question here. So, how does equipment capability factor in? Can customers run into the ceiling where process demands more than the equipment was designed to deliver consistently?
You can look at, is the frame capable of being upgraded with its auxiliary equipment that goes with it? So can I put a bigger motor on the classifying section or the grinding section of something? But we might have to change the airflow going through the system, because I can only do so much. But then if the volume of air going through there becomes so great that the velocity at which it's traveling starts to carry the product differently, then you just have to go to a bigger frame size. There are limits to the throughput for every machine out there, and you have to go to the next frame. But you can take the same frame sizes and optimize a little more with some upstream and downstream equipment and a few changes that might have to happen to make sure that your flows and pressure drops across a system are consistent by adding or taking away some different pieces inside the mill. Sometimes you just got to buy a bigger mousetrap, right?
So here's a question for you. What's something customers feel confident about when they come to CPS for optimization help, but ends up being much more complex once you really dig into the process?
It's interesting in that respect too, because some customers will come with machine X and a certain way of making their particular material, and might be convinced that it's the only way. But with our experience, sometimes they're right. Absolutely. It's the right unit. But now we know what the other affecting parameters are. If it's not the same each time, we're not doing our job. If we're not making the same product that you want each time, we're not doing our job. And we're looking at controlling all of those variables that have that real high impact on what's going on. Sometimes, though, they might come in with a style of mill or a style of blending that they believe is correct, but for sometimes the same or less energy, they can get much more throughput. One, for instance, was done with a certain style of a mill with a customer, and we said, well, if you allow us, we will try this other method. We know it's going to work. And it saved 240% of power. We got the same throughput rate, but we cut the power consumption by 240%. And the neat part about what we did there was our end result was much more consistent. From the first gram out, any sampling anywhere through that whole continuous process of the materials we're putting through, all the way to the end, very tight, very consistent, all the same. And that's what I'm happy with doing. That's what our engineers love doing. That's what made us real good at what we do, is taking what do you want, not what have you been making, but what do you want? I mean, somebody said the other week, what do you mean, what do I want? Nobody's ever asked me that before. They said, this is just what you get. And I said, no. You can make this machine do what you like. We're the puppeteers. We'll make that thing do what it's got to do. And wow, if that's the case, I'd like it to be a little more dense, and I'd like it to be a little tighter on top size, but I want these fines out of it. Okay, if you're willing to do this, this, and this, and we can make that happen for you. We give it to them, and my biggest happiness is watching the customer go back home and say, man, this is working better than anything I dreamed of. I never thought we'd get there this fast. And that's cool. That's fun.
Oh, that's great. So you're leading into, what good batch optimization actually looks like. So when batch optimization is done well, what does that process look like? Can you walk us through how CPS approaches it from initial assessment through to a stable, higher throughput process?
Start with asking questions. And it's the what do you want? And we have a whole document that's been built around that I've been using for well over 40 years, and we've been instituting it right from the beginning. What are the critical parameters you would need to see? And we will attempt to put it in the right mill with the right settings and the right process and the right variable to make what you're looking for. Some people get so critical on exactly what they're looking for that throughput rate might suffer or cycle time might suffer. But that's where we can come back in and say, okay, this is the exact thing you need, but what is the critical parameter that's going to make your product work well? And then we'll focus on taking all of those other things we'll keep in mind. But if there's one critical parameter, be it top size or average size or density or shape, we'll focus on that and make it commercializable, that it becomes, okay, I'll show you how we can increase the throughput rate on this by maximizing this one parameter, keeping in mind the others, but not making everything happen perfectly, but within usable tolerances. And that's what makes the people happy with that. And that's why our focus is, what do you want? Let us figure out the best machine to put this through, and we can then make it commercializable. We know that if we make exactly what you're looking for, but it costs $1 million a kilo, you're probably not going to want to use that. So we have to make it commercializable, and we keep that in mind and go with it. I had a customer, they had a metal that they were looking to disperse, and they said, it's too big. We'd love it small. We know that's what keeps the suspension going over time, but make it as small as you can. And I said, you got to be careful what you ask for, because it said, no, just make it as small as you can. Here's the money. Do what you got to do and make it happen. And we made it small. We made it so small that they came back to us a month later and said, we're still waiting for it to drop out of suspension because we need that for our next process. I said, I told you.
Yeah.
How small do you want it? They said, well, not that small. So, okay. It's asking those questions from the beginning. So we made it larger. We designed the right particle size with them to have it drop out over a specific amount of time. And voila, we had a commercializable, useful, very happy product for a very happy customer.
Great. So how do you determine which process parameters are the ones you can push without risking spec drift versus those you need to treat as guardrails?
If you're looking for watching the top size and you want to push everything, it might turn into a few more fines in the system. So if you're not cognizant of what that is, you have to watch it all at one time. If you're looking for really turning up a mechanical unit and heat generation becomes a problem and it starts to deform chemically the product rather, that you got to watch. So like I said, it's a whole ecosystem of processing that has to be watched all at the same time. These are good questions, but you have to look at the thing holistically. I mean, if you want to just put a lot through until it fails, you'll just have a lousy look at distribution with very non-repeatable particle sizes. You can overload a system to the point where the variation in operations of all of those parameters I'm talking about become pushed, that they're not even anymore. And then you've exceeded the limit of that particular unit. But the neat thing is what we have in our shop, we can always go to a bigger unit.
That's right. So what role do feasibility studies here or trials play before committing to full optimization? You know, is that a step often skipped, do you think, or what's the cost when it is?
Doing a trial, a benchtop trial, of looking for what the customer would like in its particle or its dispersion or its blend. That's the part one we always look at, and that's what usually the initial research and development people from these companies come in, and they're happy if it gets there. Then the business people come in and say, well, how can we make this more affordable? Well, okay, this is what we're going to do for you. We can run it at different parameters, showing you what power we're going to be using or throughput rates we get for each of these slightly variable processes. We can make it a little bit bigger. We can make it a little bit smaller. We can make it a little more wide in distribution. We can do it under a little higher heat. All of that reduces some cost, but then you're going to want to take those particles back and say, okay, this is a 7 micron and this is an 8 micron. And that might be right at the critical grain boundary point where something needs to be, is very difficult to process because you're not cracking grain boundaries anymore, but you're cracking the actual grain. And it's not linear for how much energy would go into something. It takes a lot more energy to make something, to break apart a grain than it does to break apart a grain barrier. But in those cases, we can say, okay, if you can live with 8 microns versus 7 microns, we can do this 3 times as fast. And those are the types of things we help a customer with. Oh, that's great. Sometimes they'll come back and say, nope, there's no way, I have to have 7 or below. We'll say, is there any way we can work together on finding a raw material source that will allow us to find something with the smaller grains, and we'll break apart those boundaries? Oh, yeah, we can do that. Or this is full of oils. How can we remove the oils from something because it prevents us from doing a lot of ultrafine grinding? We can find ways to remove those oils from something or moisture from something, and all of a sudden it grinds much faster, much better in what we're doing. So taking a trial to see if it's feasibility, that can you do this to what we want? Yes. Then going into on the bench or a pilot size, you can go and get, especially on a pilot size, you can get a real good indication of what it's going to do to process the material going forward on a larger scale mills. And then we take a production trial and we prove that this is exactly, we know it's going to work, but we prove to the customer this is what's going to work. But then they've got many kilograms or tons of material that they can try in their process to validate their system with the particle size or the shape or the density or the dispersion, dispersibility of the material that we gave them, all in their systems. It's a step that some people say, well, this worked, just go right to production. But then we can figure out in production, it'll take a little more time. You'll use more material, obviously, to do that, because in a pilot scale, we can do it with a few thousand kilos. On a production scale, you're talking a couple of truckloads of how to do something like that. So there is a benefit of working from benchtop to pilot to production, unless we've already got real high experience and high confidence with materials. Because like I said, I've been doing this for over 44 years. Custom Processing Services has been doing it for over 25 years. We kind of know what we're doing and how to make something happen. And we can save a lot of time for people on stuff we already know about.
Everything you have said today, brings me to this point where process monitoring and data collection seem to be very critical here, I would think. So how does CPS use real-time data to catch drift early before it becomes a spec failure?
Knowing what to measure is key at first. I said there's design of experiments we've done to set some parameters. Some of those are fixed parameters. It's the size of a piece of, it's the size of a particular part of the mill that we insert or change out as necessary. But temperatures, pressures, airflows, kilowatts, weight of material inside the mills, the work we're putting into it, we measure in a real-time basis with data collection systems. Up to 3 times a second we're measuring these things. So as we know what the upper and lower control limit should be on that based on how, first of all, our calculations that we've done, we know by calculating where that upper control limit will be. And we confirm it by doing viscosity tests or particle size tests or moisture tests or whatever else. We confirm it with that, but we know what parameter in that mill or blender or disperser will give us as an output. I liked doing this with a very fine product one time. The customer was there and we were making 5.7 microns. And he says, I need 5.2. We calculated it out. We plugged in the parameters, and I threw it to the lab. I said, there's 5.2. Well, it can't be. You don't know that. We didn't test it. I'm saying, yes, we do. We know how these machines work. We measured it. We kept it in those parameters all along, and sure enough, it came out at 5.2 microns. Told you. So if you're measuring all of the elements that make a particle the way you want it, or dispersion the way you want it, or a drying operation the way you want it, if you're measuring the right parameters and know which ones affect mostly what parameter you're looking for in a final spec, you control them. So not only do we data collect, it feeds back into our system what parameter changes we have to do to keep them where they're supposed to be to make those final products properly.
So let's talk about CPS's role as the energy sector toll processor.
Okay.
So, the energy sector is growing very fast. So how has this growth in batteries and energy storage and advanced materials changed what customers need from a toll processor like CPS in terms of batch optimization capability?
We have many different customers, and nobody is doing something the same way. So we found this as a big opportunity for us to help any of these battery storage manufacturers, storage battery manufacturers, to help them create the right matrix of material, the right anodes, cathodes, separators, and whatever else they need. Because we have lots of installed equipment. We have real good understanding of the cause and effect of what a machine will do to with a certain product, a certain raw material, and how it would act and how it would move along. So working with these companies individually to really get, and I'm going back and telling the same story, get their idea of what they want, we can find the way they need to get it done properly. I had said earlier that some battery systems need larger particles, some need smaller. Some want to try the benefit of a denser material. Works great, but it only transfers power for so long or doesn't recoup it. We're working with people, with customers, with companies that want to really drastically reduce the charge time of a battery to where it's like pulling up to a gas station today, or you can fill your tank where you can fill up your battery to maybe 80%, but in that fast. And there are certain products that go in there that have to have a certain morphology. It's the raw material that our customers have figured out what they want to do in this matrix, but it has to have the right morphology, size, density, shape, everything else, and we help them. So what do you want this to do? We'll help you build to where your energy and your power numbers really work out well. So nobody's building it identically the same way anywhere, but there's always a certain characterization of one of the raw materials or many of the raw materials and how they can all react together that create that matrix that makes this particular system work well. Why can you come to us? Because we've already got a variety of machines. That's the neat part. I've always reinvested and bought more toys to do more stuff. But so we can reduce that development time because installed capacity, knowledge of how to use it. You can buy a machine, you can put it in your lab, you can put it in your pilot center, and you will spend lots of time trying to figure out how to put it together, how to run it, how to optimize it, how to make it work, only to realize this machine isn't quite the right machine to do what we need to do. Okay, now let's go find another one and set up and repeat the whole thing. Whereas we can say, okay, in our one station, we have on our trial station, our pilot station, we've got the ability to pull in and plug in a variety of different machines. What we believe will work from our experience, because we're saying, okay, what do you want? I'll make it like you're looking for. But as they're going along, if there's a new understanding of what light bulb goes off in their head saying, man, well, if I only made it look like a round particle instead of a flat particle, this would work a whole lot better. I didn't realize that. Okay, let me put a different machine in. We'll make that and watch your battery system shoot to the top. So we can shorten that time frame to do something because we have a variety of material, variety of machines. We have a variety of experience, and we can do it in short term because it's already installed.
So, you're kind of touching a little bit on, CPS's role here. So what do you think CPS brings to the table, specifically for the energy material customers that a general contract manufacturer might not? Do you think it's equipment, process expertise, both?
Both, because it's a variety of equipment and the expertise that we have and some slight modifications that we can always make to equipment for a particular customer's need. We don't have to start from scratch and put in a large $1 million system just because, a new one, because we know what it takes to do this particular customer's material. We have the basic framework of all of these machines that for a specific item, it might be a certain style of feeder or packing system or pressure allocation system that we put through it, or sometimes just making sure it's got the right kind of blanketing that would have to happen with certain materials. All of those are just smaller add-ons that we can do for a customer and do it very well. So A is the equipment. B are the engineering groups that we have. We have what we call technical sales engineers. And these are the folks that say, aha, yes, I have, you have a process that you had been using or you think you can use, but you have a material you want to make something into. This is where they get excited and be able to use this palette of mills that we have, choose the right ones. They get together like a bunch of doctors get together and discuss a patient. We get together and discuss the best way to go about making this your particular product the way you want to, and then we put that in there. It saves a lot of time. It saves a lot of repetition. It saves buying the wrong piece of equipment if you try to do it in-house or yourself. Even if you've been doing it one way for a while, you might find that with new advances in some materials that become available, you might have to start doing things differently, and we can do that. And that's what CPS can bring to the table. The already installed machine capacity, the engineers that can make those machines do whatever the technical sales engineers wish to do, and the technical sales engineers taking what you want and making it happen because they know how to make those things fly. It's your own research and development company right at your fingertips.
That's great. So, tight specs and high throughput are table stakes here. But what about consistency batch to batch over a long production run? How does CPS's approach repeatability for customers with ongoing supply needs?
That has been the key to our success right from the beginning. We will set a target and we will hit those targets. And because we know how these machines work and we monitor all the critical parameters that go into that machine, and we can, like I said, normalize some raw material differences. We can normalize to a right particle size or shape or density for you. But we target a spec. And if you want to change something, change the target, because otherwise our systems are controlled to maintain that particular target. It was really cool where we had a customer back in our origins in 2000. We still have one of those samples, and we're still making that product today. And I said, come on, let's pull this 25-year-old sample and we'll compare it in all of the quality parameters that it's supposed to achieve and see if they're still the same, because this is one product we never changed spec on. And they overlaid. I mean, it was like a glove. It was amazing. So we prove what we say. We operate these machines to maintain a specification all the time. And unless you change that spec, we will not. And that's critical, because for what these go into and the uses they have, if they're not working perfectly with the rest of that system that they're putting these materials in, it could screw up everything. So our consistency is critical.
So how does the tolling model work to a customer's advantage here? Is there a flexibility or speed benefit compared to building or retooling in-house?
In-house, there might not be the expertise that we have on all of these machines inside of a manufacturing facility. I know how to feed it, I know how to turn it on, and unless you're surrounded with engineers that help and understand how all these interactions take place, you're going to have a harder time making that. So tolling something, processing it, custom processing it, we have this expertise built in. We know exactly how these machines work. We know the theory of the operation. We know all the calculations of the theory of operation, and we put them into practice. So that's how we get a consistent product. Unless you want to change it, we'll know exactly how to change it. But we do this 24 hours a day, 7 days a week, and we've been doing it forever. We know what it takes to make this happen. In some other facilities, especially for those that are not using some products, filling up a machine every shift of every day, that experience isn't there. Oh, once a month we run this for a week. You don't really get that expertise, and you don't really give it that specific attention that it might need to optimize that and make sure consistency is there. Whereas we know it because we do it every day, and we know where the faults are of the machine, and we avoid them.
So for operations leader or process engineers who currently struggle with spec variability as they try to increase throughput, what would you say are first two or three things they should evaluate?
Make sure you have a real good understanding of what your materials you're looking to process are in every respect. Don't just look at a specific particle size of a D50 or a top size of a D97 or 100, but what is its density? How does it flow? What is its moisture? What is the shape of the particle? What is the distribution of those particles that go in there? In blending, what is all of those things, plus what is the consistency of the way the materials are mixed together? Are they lumping? Are they clumping? Are they not supposed to do something like that? All of those items, you got to know your material, and that's what we do. A big thing. The first step before we ever put it on any machine anywhere is really understand what the powders or the liquids or the different varieties of raw materials you're putting in there, what they really are, and understand them. And then if you're trying to increase that, what particular item is very important to you, and put the power in, or put the airflow in, or put the volume in of size of the unit to make sure that those are watched. But don't forget about the other ones, because all of a sudden it might upset something downstream that you never even thought of before. So what could be a written specification might have hidden specifications because it's been the way you've been doing it for a while. Whereas when we're doing it, we watch all of those parameters. And if something does have to change, or does just because of the physics of what happens inside of a mill as you add more power to it, we can warn people about that right from the beginning and fix it by putting it into a larger mill, or rather than just adding a lot of power and breaking the particle apart differently, or smashing it into agglomerates, or adding so much heat that it reabsorbs moisture. Those types of things we look at consistently. But if you're in your own plant and you're looking at those things, pick your important one, but watch the others so you don't ruin the products downstream.
So at what point should they stop trying to solve it internally and bring it in a tolling partner? What are the signs, would you say, that outside expertise is the right type of call?
Well, if you don't know about the machines, and God bless everybody that's out there, there's a lot of process engineers smart as whips. They just don't have the familiarity with the machines that they're working with to the degree that we've got. I mean, it's just there. What you don't want to do is break the machine. We've seen that happen. You don't want to ruin product to the point where you're shutting down the rest of your plant, because that would be really bad. So working with someone like us, I'm not really going to come into your plant and tell you how to go do that. But if you would like to come in and process material with us, we can get it. We can let you know if that's a possibility of making something at a faster rate than you're making already.
So as we wrap up, what's one thing about batch optimization for advanced powders that customers should understand but typically don't initially?
It sounds simple, and I've said it before, but it's understanding all of the parameters of the material you're starting with. If you know that, you'll know what to change going forward. It's a real inspection, testing, completeness. Get to know your material, become one with it, and you can then solve a lot of problems that way.
And lastly, what's one commitment you'd want every energy materials customer to make before they try to scale production output?
In my plant, if I'm going to try to scale something, I want to make sure that if I know we're going to add more energy, or you know you're going to add more energy, that if you have to change a processing parameter, like I said, either flows or pressures or temperatures or speeds or whatever it is, go back and put it in a small unit to validate, verify, create those particular high operating parameter changes and test them in the matrix of what you're going to use it in before you go ahead and put it in a larger machine, to make sure that when you add more energy per unit, but it gets more throughput, does it change something else about the product? And if you do it in a little bit and you catch that, you say, "Whoop, I can't do that. I didn't waste 3 weeks of clean outs and how many batteries or how many tons of mix I've got to put together. I've done it on a small basis." Before you do it, try it, but understand what you're changing in your larger mill, or what you would be changing in your larger mill or in your current mill, but what parameter would you be changing? Go back and look at that in a small one to verify you're not going to mess something up. Record all your operating parameters, and then it will scale if you are watching those particular items.
Great advice. So this has been a really great conversation with a ton of great insight. And so I do appreciate you, Gregg, for coming on with all your expertise. And thank you to everyone tuning into this episode of Toll Manufacturer Minute. If you're working with high performance energy materials and need a processing partner that understands both the throughput demands and the spec precision those materials require, CPS is always ready to help. And be sure to subscribe so you don't miss our next episode, and we'll see you then.